After front-end compression, let's take a look at the back-end compression. The first method we talk about here is low rank. We think the conv is actually matrix computation, and we know that a matrix could be decomposed. A very big matrix could be represented by some low-rank matrices approximately. For example, in PCA, we have a 300 times 300 matrix. We could usually use two 20 times 20 matrices to represent 95% of the information, and the rest 5% information will be thrown away. And the matrix have been compressed to an extremely small matrix. In low-rank neural network, it's very similar to PCA. For example, I have an n times n conv, and I decompose it to two matrices, and the dimension of those two matrices are n times 1 and 1 times m. Their receptive fields are the same. This method is proposed. The main idea is to decompose a d times d conv to d times 1 and 1 times d conv. Mathematically, a d times 1 matrix times a 1 times d matrix is a d times d matrix, but a d times d matrix has d times d parameters. But after decomposition, there are only 2 times d parameters. Both number of the parameter and flops have been reduced significantly, and the experiment shows that the accuracy loss is less than 1%. So this is a very interesting idea. The receptive field doesn't change, the represented matrix doesn't change either, but the number of parameters and flops are much smaller. Another idea is similar to PCA, which uses SVD. We could do SVD for a conv computation, and we keep the large eigenvalues, and the math formulas are just normal SVD formulas. The first step is to SVD the matrix, and then the second step is to rank the eigenvalues, and I only pick the large eigenvalues. 1,000 times 1,000 matrix could be compressed to 100 times 100, so the computation is greatly reduced, and we call this kind of network as SVD network. Besides low rank, which is simple and straightforward, there is also a frequently used backend compression method, which is pruning. We assume a network was fully connected, but many connections and neurons are actually redundant. After training the network, prune out the parameters that contribute less. If the weight is small, then after activation, the effect is very small. Prune out the connections if the weight is small and make the network sparse. Like this network, it was fully connected, then I noticed that those two neurons are actually redundant, so I prune out those two neurons and the corresponding connections. This is the main idea of pruning, and the procedure of pruning is here. I first measure the importance of a node, and then I prune out the unimportant node, and then I fine-tune the network because the structure of the network has been changed, so I manually change the weights of this new network, and then I go back to step 1 and start another round of pruning until the network is small enough or there's no neuron could be deleted. There are many types of pruning. The first type is fine-grained pruning. This tensor is a conv. If I have 3 different convs, I measure every single parameters of these convs, whether they are important or not. The second type is vector level pruning. It means that instead of one by one measuring, I measure the importance row by row, and that is vector by vector. The third one is kernel level pruning. I will either pick or throw away k times k kernel. The fourth one is group level pruning. For each tensor, I will throw away the same location's parameter. And the last one is filter level pruning. I will either pick or throw away a full conv. It means that the output feature map, the 13th channel, is gone. Pruning method could be classified as 3 types. The first one is weight decay. As we mentioned before, to get rid of overfitting, we will add a regularization to loss function so that the network will be sparse, and then prune out those neurons with small weights. For example, prune out those weights with weight smaller than 0.1. But the drawback is that it's highly sensitive to the weight threshold. Should I delete 0.1 or 0.001 is a question. If the threshold is not well chosen, the network will be broken. The second one is sensitivity evaluation. The main idea is to create a sensitivity matrix, evaluate the importance of each neuron to the network loss. If the neuron doesn't change the network much, then I consider it as an unimportant neuron and I will prune it out. On the other hand, if the neuron will greatly affect the network loss, then it's an important neuron and I will keep it. The third one is prune-based relevance. It's similar to PCA. If I have two nodes and they are highly correlated, then I could merge those two nodes or delete one of them. Let's take a look at weight decay method first. The first thing we need to do is to add a regularization to the network loss. There are two regularization methods, L1 and L2. The main difference is, do I want the L1 of W or L2 of W to be as small as possible? After adding regularization, the network will be sparse. Then I set a threshold and filter out those nodes whose weights are smaller than the threshold, and then fine-tune the network. Go to step 1 again. The drawback of this method, first of all, I don't know what threshold is good, so I usually will give a lot of thresholds and try multiple times. Second, the threshold is shared by all layers, and this might not be appropriate. Because the shallower layers and the deeper layers might need different thresholds, it's hard to pick up one threshold that suits the whole network. What's more, it's not friendly to hardware. If we train models on servers, that could be okay, but if we train on FPGA, it won't be very well supported. The second method is sensitivity evaluation. The procedure is like this. I need to train a model, and if I want to prune a node H, then H equals to 0. We evaluate its importance to the network loss, and CD is the network loss. We could get its condition probability, W is the weight of the network, and H equals to 0, meaning the node is pruned. Then the tidal expansion is the later part. If the node is not pruned, then the possibility is CDW, and then minus the loss to H first order partial derivative times H. Then plus the high order terms of H equals to 0, and this high order term could be ignored. If we use loss when H is not pruned minus the loss when H is pruned, it's the loss gap, which is also the sensitivity. So the loss function to H first order partial derivative times H is the sensitivity to the node H. If sensitivity is low, we prune out this node, and then fine-tune the network, and then repeat step 1 to step 4. The third one is prune based on relevance. If I have two nodes I and J, I'll calculate the relevance between those two nodes, and there could be 5 outcomes. The first one, the two nodes are highly positive correlated. The second one, two nodes are highly negative correlated. If they are highly correlated, I could merge those two nodes, no matter if it's positive or negative. The third one, two nodes are not correlated or not highly correlated, then I will need to keep both nodes. The fourth one, one node's covariance is small. It means that whatever input it takes, the output is almost a constant. It means that the node doesn't change much. And we could directly put a constant to connect to the other nodes. The fifth one, that the node's covariance is big. It means that this node is sensitive and it contains much information. There are other methods which are hard to classify as one of the three. This method is prune based on gradient, as the gradients are also various, could be big, could be small. If the gradient is almost 0, then I won't update the node, and it is concluded that there is only 1 to 4% of the weights need to be updated. So there are more than 90% of the nodes that don't need to be updated. So the training time will be much faster. And it's a proof that the accuracy almost is the same. Another method is called network slimming. It associates a scaling factor to each channel. It's like adding a channel attention between the input and the output feature maps. You could consider it as 1 times 1 pointwise conv. In training, these channel scaling factors are also trained. And those scaling factors with small values, I will prune them out. I will also delete the corresponding feature map. The last backend compression method I will introduce today is quantization. It is widely used in hardware. The weights of the network are usually float 32, but we don't really need that precision. Instead, we could use 2 bits, 4 bits, or 8 bits to represent the weights, especially in microcontroller. It prefers int compared to float. There are binary, ternary, multiple bit quantization. Quantization could apply to weights, features, and gradients. The first one is binary quantization. A very classic one is binary weight network. There are 2 ways to make it binary. One is based on sign. If the parameter is larger or equal to 0, then set it to 1. Otherwise, set it to -1. The other way is based on probability. I first define a probability formula, which is max 0, mean 1, x plus 1 divided by 2. When x equals to 1, then it is 1. So the probability function output is 1. And when x equals to 0, it's 0.5. Then there is a 0.5 probability that it will output 1, and there is a 0.5 probability that it will output -1. So it will have a bit randomness, unlike the first method where the output is always settled. After making the parameter binary, for next step, how do we train the model? Because the function is not derivable, when x is larger than 0, the gradient is 0. When x is smaller than 0, the gradient is also 0. And when x is equals to 0, the gradient is infinitive. To solve this problem, we change the function to this one so that we can get the gradient. We change the sign function to this. When x is larger than 1 or smaller than -1, gradient equals to 0. When x is between -1 and 1, the gradient equals to 1. And the gradient is also an integer. Next one is ternary quantization. This is an example of ternary quantization. It uses -1, 0, 1 to quantize the network. There are 2 steps. The first step, it quantizes the activation, which are the feature maps. The second step, it quantizes the weights. So how to measure the quality of the quantization? Is it good or bad? It hopes that the output after quantization should be as similar as the original float output. So it tries to solve this optimization problem. And this could also use loss to propagate back. And the ultimate goal is that the output of quantization should be as similar as original float output. This is another quantization method. The normal weights and normal gradients are those colorful matrices. They are float 32. I cluster them first, and then we will have the cluster centroids. For example, I cluster them into 4 groups, and there will be 4 centroids. So originally, I had 16 times 32 bit float, but now I have 16 times 2 bit matrix and 4 float 32 centroids, and so it is greatly reduced. Same for the gradient. I cluster them first, and then I get the centroids. So after updating the first number, the first class will be 2 minus 0.04 equals to 1.96. And originally, for the first number, it will be 2.09 plus 0.03, which is 2.09. 1, 2. So those two numbers are quite similar. So for the second one, it will be -1 plus 0.03, which is minus 0.97. And the original value should be minus 0.98 plus 0.01, which is also minus 0.97. So sometimes there's a difference, but usually the difference won't be too large. This is a very interesting idea. The main idea is that I first cluster the weights and gradients, and then give index to clusters, and finally update network based on the index. It will be different from the original float 32 network, but the difference is very small. Here is a summary of some quantization methods. For example, BWN, it makes the weight binary, the activation is full, gradient is full. It doesn't happen to training, but it happens to testing. If you're interested in quantization, you could refer to this chart and dive into these methods.